Hi, welcome back. In this video, I want to have a look at memory circuits. Now, we're not going to be making any hard drives. What I'm doing is I'm simply making a circuit that remembers a bit of information. When the circuit is powered off, that information is lost. And this will be used, for instance, later on when we look at finite state machines and counters and things. We need circuits to remember the result of their previous calculation, for instance. Okay, so this is a latch circuit. It's called an SR latch or an RS latch. And I just want to have a look at this. I have this built here, by the way. So I'll look at that in a second. But first of all, I want to look through here. So this is a NOR gate. And what that does is it's an OR gate. So it takes two inputs, does an OR operation, and then it applies an inversion on that operation. Now, this circuit might be a little tricky to reason about because, as you can see, the output of one gate is the input, and then that then becomes the input of the next gate. So here's a shortcut. Anytime I see an OR or a NOR, I know that when there's a 1 on one of the inputs, that forces the function to have a certain response. So for instance, anywhere where A is 1, I know that this gate has to be high, then it gets inverted, okay, and then we can work from there. So for instance, let's go from the bottom. So when A is 1 and B is 1, we know that we're going to have a 1 here, and then that becomes a 0. We come in here, there's a 0 plus a 1. 0 or 1 is always 1. So then this bit becomes 0, and then it doesn't matter what this bit is. And so we're going to have a 0 on both of those. On the other hand, when A is 1, we know that we'll have a 0 here, and then this 0 comes along, and then it's 0 or 0, which is 0. That inverts to 1, and then I can just double check that. If a 1 comes back in here, that's fine. 1 or 1, still 1. Goes to 0. So I think it's useful to check a few of these oscillations and check that there's nothing funky going on. But here I can see that C would store 0 and D would store 1. Okay, now let's have a look at the case where B is 1. So B is 1, that comes in here. 1 or anything is 1, inverts to 0. And then 0 comes back here, so we have 0. And then it's 0 or 0, which is 0, inverts to 1. So we have this 1, 0. Okay. Now, let's say we're in the case where both A and B are 0. Well, that's tricky, because if I take 0 or anything, it's like that 0 doesn't matter. This C and D will now really depend on the value that C and D had at the last time step. So what I'm going to do is I'm going to say, well, what if C was 0? What will it become? What if C was 1? What will it become? And I'll do the same thing with D. If C is 0 and D is 0, let's say that, then we'll have C is 0, then we have 0 or 0 will come through, and this will become 1. So then D will become 1, and then 1 comes in here. 1 or 0 will be 1, inverts to 0. And so we get that when C is 0, becomes 1, and C becomes 0. Now in C is 1, we have a 1 coming in here. 1 or 0 is 1, inverts to 0. So then D becomes 0, and that 0 comes back. We have 0 or 0 is 0, inverts to 1. And so what we get is that if C is 0, it stays 0. If C is 1, it stays 1. And then if we look at D, this is a lot of fun. We look at D. If we have 0, we have 0, 0, so 1 here. So C is 1, and then this comes back. 1 or anything, 1 goes to 0. Okay, and then if D is 1, we have, come in here. 1 or anything is 1, goes to 0. So C goes to 0, and then we have 0, 0. So there's two really important things to note. One thing is that C and D, turns out they always have opposite signs. And then the other thing is I went through this case, and then when A and B are both 0, whatever these values are, they are stored. They're remembered. Because we can keep doing that loop forever and ever. It'll still be the same. So how does this match up with the RS latch? Well, typically we wouldn't use C and D. We would say, okay, Q is the bit that we're storing, and it just so turns out in the logic of the latch, we also have Q's inversion available to us, because we always know that those two lines are going to be the opposite of each other. And now if we look at how these inputs affect Q. So when B is high, Q is automatically set to 1. Except in this case, and this is dodgy, and we'll see why in a second. Okay, so we ignore that case. So I'm going to call this S for set. And then A, when A is high, Q goes to 0. And so for that reason, I'll call a R for reset. And so here we have our RS latch. When we send a pulse along, it will set or reset the value of Q, the bit that we're storing. And when we send no pulse, it's not remembering anything. So I think it's really important to emphasize this. When you're building a circuit, always read the data sheet of the chip that you're using. For instance, I'm using this CMOS chip here, and I hooked it up. This is a NOR chip. I hooked it up and it just wasn't behaving the way I expected. And I was really doubting myself until I looked up the data sheet. And if we zoom in on this, you'll see something funky. Usually these gates would all be going the same way. It definitely was in the last video. However, in this video, in this chip, and in this video, it's reversed. So that's just very important very important thing to pay attention to. But anyway, onto the chip, or the circuit even. So if I read this from left to right, here I have my reset, my set, and this will be my Q and my not Q. So we can see at the moment, this circuit is storing a value of 0 in Q. All right, so let's set Q. Boop. There we go. Now Q is on. Great. Let's store that. Okay, so Q is still on. Let's go ahead and reset Q. It's off. And let's store that value. There we go. Still doing it. So by setting or resetting, we are changing the value of Q. And if we do nothing, keep them both 0, the original value is still stored. So now the exercise that the challenge I want to put on is, how can we change this so that instead of having to manually set or reset, we can just have a single wire and its value gets stored. So instead of this, I'll actually do a modification of this. So put some space here. I want to have like a data line. That data line can be 0 or 1. This is the value that we're going to store as Q in the next time step. And I'll go ahead, I'll call this a clock. And the value of D will be stored when clock is 1. And when clock is 0, we can change D and the circuit won't change. So take a second to think about that, how we can use that information with this information. Okay, how did you go? Oh yeah, not bad. So here's what I'm thinking. I want to do this. So if I take D and I hook D up directly to R, then that would be storing the bit when D is high. Now when D is low, I want to set the other signal high. So I'll just invert D. Okay, so there's that. But then the question is, how do we set it so that this is only happening when clock is high? Well, remember, that's an AND gate. So what I want to do is I want to take this and the clock pulse, and likewise I want to take the clock pulse and AND it with that other signal, and I want to send this result. I think I'm used to it being the other way. I want to send that result, the positive case, to set, and I want to send the negative case to reset. Now, this is a bit of an ugly diagram. Yeah, that's fine. I'm just going to take a second to build this circuit. Just like for the adder circuit, this is not going to win any awards for prettiness. However, I did get it done. Now, I've got the data sheet up at the moment because it's super important to note, always look at the data sheet for every chip that you're using. I was using this AND gate and I just wasn't getting the expected result. So I looked it up and it turns out that it has a similar thing going on to it as the NOR gate. So if we look at the pins 1, 2, and 3, we see that they form the first gate with 1 and 2 being the inputs, 3 being the output, whereas we would probably, from the past video, think 4, 5, 6, 4 and 5 being the inputs. If we actually have a look at the next gate, we see that it actually goes the opposite way. So 5 and 6 are the inputs and 4 is the output. But anyway, let's have a look at this. So here we have our circuit. This first line is the data. So this is the data that we're sending in. And the second line is the clock or the enable. So we can see currently the chip is, well, the memory cell is enabled. So whatever we send on the data. Oh, that's fine. let me just take 1 second. I had this LED unplugged because I was debugging things. I was using it for debugging. So here we can see that currently the chip is enabled, the input is high, and we're storing that high signal. Now if we disable the chip, there we go. If we disable the chip, I can now change the data, but we're still storing it. It doesn't affect it. The brightness changes, could be a current issue, but it's working. Okay, now currently we're sending in no data, so let's actually enable that chip to remember no data. Great, so currently we see the chip is enabled, Q is low, Q bar is high, and our data is low. Now I'll just disable the chip. We still see Q is low, Q bar is high, and now I can, fingers crossed, change things around. So I'm sending some data, but we're still not remembering it. Again, brightness changes. It's an electrical issue, but yeah. Okay, so now some data's coming in. If I now enable that chip, we've got it. So there we go. That's just been a little adventure into memory. I hope you had fun. The really big thing is to note how we start from first principles and then modularize it and go from there. Okay, so all the best, have fun, and I'll see you again soon. Bye.